So this is second semester performance task review. We've got an open top box is to be constructed from a 12-inch by 14-inch piece of cardboard by cutting out the corners here. And we want to know how much needs to be cut out of each corner to create a box of maximum volume. So we've got 12-inch by 4-inch, so if this is 12 and this is, or by 14-inch, this is 14. If each of these corners are x by x squares, then what we have down here is from here to here, is a 14 minus 2x. And up here, from here to here, is a 12 minus 2x. So if I think about this in terms of volume, I have volume equals length times width times height. In this case, the length is 14 minus 2x. The width is 12 minus 2x. And the height is x. So to find the maximum volume and to find the dimensions of the box with that maximum volume, we'll take A and B all together. We're going to need to plug this into our calculator and use the max feature on there. So I'll show you how to do that. So on here we're going to type in 14 minus 2x times 12. I wouldn't even bother distributing it, just type it in just as we wrote it out, times x. So that's our function. And hit zoom and Z standard and have it graph it. So this will be a cubic. It's three-dimensional. We can see that the max looks like it goes up off the screen there, but our max that's in a reasonable domain between 0 and 6, which is what we'd want. If you go back to the picture here, I can show you why the domain is 0 to 6. The biggest that x could be here without going into negatives would be 6. If it could not be 6, you would have a width of 0. So our domain, the reasonable domain, would be maybe open 0 to 6. So something between 0 and 6. So if I go back to my calculator, it doesn't matter that it doesn't show up on the screen. If I want to, I could adjust the window if I'd like to. Maybe adjust the window so that the y max maybe goes up to 80 or something like that, and hit graph again. Let's see if it'll show up. But either way, it doesn't matter. You can still, it's still not enough. You get a better picture of it. It's just above there. You can see that somewhere around here, up here is our max, somewhere up here. So if you go to second, calculate. And let's see, second calculate, and we're going to hit number 4. And the maximum, it's going to ask for a left bound. The origin is a good left bound. It's going to ask for a right bound, so I'm going to take my cursor and get it till it comes back onto the screen here. See, my window should have been here. It's coming back down now. You can see the Y went up to 160. Now it's coming back down to the 140s, 130s. And more clicks here. There it is. So that'd be a good right bound. Then I'm just going to left arrow one time, make sure I'm in that interval somewhere between 0 and 6. Hit enter. It'll give a guess. So the maximum is x equals 2.148. 2.148. Maybe we'll round to the nearest 100, so 2.15, and the max volume is 160.58 cubic inches. So what is the max volume? We can answer that right away, 160.58 cubic inches. And the dimensions, if we know x is 2.14, we can then plug in quickly and find the other two dimensions. So plugging in 2.14 right here for x, and then plug it in here, that'll give us the width. Plug it in here, that'll give us the length. So 14 minus 2 times 2.14 gives us about 9.71. So we have 9.71 inches. By, if I do 12 minus 2 times 2.14, I get 7.71 inches, and then by 2.14 inches. So those are my dimensions In other words, I would cut about a 2.14 inch square out of each corner, and that would give me a maximum volume of 160.58 cubic inches. It says, what percentage of the surface area is being thrown away to create a box with maximum volume? So that's asking of all the surface area here. If you take the whole thing, 12 times 14, that gives us 168 inches squared of surface area. And so the question is, how much is being wasted? What percentage is being wasted? Well, if we take the 2.14 or 2.15, let's just say 2.14 squared, that's one of the squares, and we're going to take that and multiply it by 4. So let's just all at once. So 2.14 squared is one of the squares. We have the product of all 4 squares gives us about 18.45. So the waste percentage is 18.45 divided by 168, which is about equal to about 10.98%, or about 11% is my waste. So that's it on that one. It says that D, if the volume of the box must be 120 cubic inches to hold an item, what size squares would have to be removed? In this case, we had the volume equaled 14 minus 2x, 12 minus 2x, and x, and we're going to set that equal to 120. So if I go back to my calculator, all I have to do is move the 120 over, and set it equal to 0 and solve that for x. So this is saying that if the volume must be 120, what size squares would have to be removed. So let's go ahead and go back to the calculator. All we have to do is go back to the y equals menu, take this equation, and we're going to subtract 120 over. So we do minus 120. Go ahead and hit, I like to start the standard graphing window and then go from there. So standard graphing window, have it graph it. And then go ahead and find the zeros. Congratulations. Yeah, thank you. Sorry. All right, so in here we just need to find the zeros this time. So we hit second, calculate. Instead of max, we're going to find the zeros. Hit number 2.
Does it matter?
It'll ask for left bound here, and so see if I can get my cursor here over on the left bound. I need to get it closer to 1. You can see it goes through at 1. There it is. So left bound, that'll work. Right bound, and whoops, like that. Holy crap. Okay, let's try that again. Second, calculate. Okay, let's try that again. Second, calculate to 0, number 2. So left bound, we got to be below that first 0. Right bound, you go up a little bit more. Right bound. Guess, we'll get something in between. So one of our values, one of our zeros is x equals 1. So as a solution to this, x equals 1 inch will give us a volume of 120 cubic inches. Or if you look at the graph here, there's one more here. So we're going to do this again. Go second, calculate, 0, and left bound. That'll work as a left bound. We need a right bound that's below this other crossing of the x-axis here. You can see there's a third crossing, but we're not going to worry about that because, oops, I think I already crossed it through here. 1, 2, 3, oh, it looks like somewhere between 3 and 4 is where it crosses. There it is. So that'll work for a right bound right there. It's just below the other 0. I guess go 1 left arrow back, hit enter, and it will give me the other place. So 3.6 inches is the other spot. That will give me a volume of exactly 120 cubic inches. So going back over here to the calculator, you'll see there's another 0 over here. This one is out of the domain. Remember, our reasonable domain was 0 to 6, so anything over 6 would not be a box. We would take out this, my picture here. Anything bigger than 6 right here would make it have no width. So those are our two values. 1 inch and 3.6 inches give us exactly 120 cubic inches. So here is the cable suspension bridge problem. Problem number 2 on there. So it says the cables of a suspension bridge are in the shape of a parabola. So we're going to make this the origin. Therefore, we have a 0, 0 as our HK. So it's y equals 1 over 4p x squared. This coordinate up here is 300, 80. I'm going to use that x and that y to find my 1 over 4p, or coefficient of x squared. So plugging in 80 for y, 300 for x, I get 1 over 4p equals 80 over 90,000. Just at a glance, I could simplify that a little bit. Call it y equals 8 over 9,000. Does 8 go into 9,000 evenly? Check it real quickly. Yes. Ooh, how many times? Oh, that makes it even better. So this is 1 over 1,125 x squared. Perfect. So now I'm going to use that mathematical model to find the height when I'm 150 units out from the origin. So y equals 1 over 1125 times 150 squared. You could leave it as 80 over 90,000 if you want. It doesn't matter, but that's kind of nice. 1 over 1125, a little cleaner. So you plug this in. What do you guys get on this for the height we are up on the cable? 20.3 feet. That's it. And then here, we've already found this relationship here. So I need to find P, the distance the focus is away from the origin. So I remember that 80 over 90,000 is equivalent to 1 over 1125. So I have 1 over 1125 equals 1 over 4P. So obviously the ones are equal. So I can just set the bottoms equal. 1125 equals 4P. So 1125 divided by 4 gives me a P value of what? 281.25. Okay. So the focus is 281.25 feet above the origin. So that's problem number 2. So on 3, we're just finding the dashed lines. Sometimes we might assume that these two dashed lines, top and bottom, are parallel, but they're not necessarily. It says you're building a fence around the backyard of your property. There's a utility box that needs to be accessible and therefore cannot be fenced in the yard. So they need to come in and be able to read the utility box. Maybe PG&E does. With the measurements shown, what is the perimeter of the fence, the dashed line? So this involves actually no right triangles here. But it involves law of sines and law of cosines to find it. So when I see this side angle side case, right away I think law of cosines defined. Let's call that C. So it would look like this. C squared equals A squared, 1.5 squared, plus B squared is 2 squared, minus 2 times 1.5 times 2 cosine of 82 degrees. So you're going to remember that you have to take the square root. To get C, you have to take the square root of this whole expression. And when you plug that into your calculator, you get around 15 yards, I believe it was a 14.99, I believe. 14.95. Okay. About 14.95. Now, to get actually, I don't think that was 14.95. I think it was this length that was 14.95. I don't remember what C was. This right here? Oh, this one is 15. Okay.
That's 13.25.
Okay. This dash line is accurate. What did you guys get for C? 2.3, okay. That sounds about right. So we've got that piece right there. So C is equal to about 2.3. Now, because this is 82 and this is 55, so we've got an 82, 55, that makes this a 43 degrees. So if I pop out this triangle, I've got this non-right triangle with an 82, a 43, a 55. I need to find on here, we know this piece over here, from here to here, is the 18. So I need to find, let's call this, I don't know, Z, and this could be Y. So I need to find Z and Y, and then once I find Z, I've got to subtract 1.5 from it because of this 1.5 yard gap there that we're going to leave to get in to access that utility box. So law of sines comes into play here. We have sine 55 over 18 equals sine 43 over Z. And that I can use to find Z. So Z ends up being about, I'm hearing about 15 yards for Z. The whole thing is 15 about. And so that means this dashed line, let's call this maybe X. X is equal to 15, which is the whole piece from here all the way to here, minus 1.5, which is about, should have squiggly equals here, about 13.5 yards. So I've got this C equal to 2.3, X is equal to 13.5. Now I just have to find this bottom piece here, and then I can add them all up. So I can reuse this sine of 55 over 18 again, and go ahead and find my length y. So let's do that next. So we've got sine 55 over 18 equals sine 82 over y. And solving that for y, what'd you guys get for y? Let me solve that. Cross multiply and divide. And we're going to add them all up. 21.8 yards. So circling that as well, we've got the total fencing is the 2.3 plus 13.5 plus 21.8, which is about equal to 24.1, 37.6 yards, I believe. So 37.6 yards.